Hello students, hope you are doing well. In this video we are going to discuss Enterprise Campus Design Part 2 of Unit 3 Designing Basic Campus and Data Center Networks for the subject Enterprise Network Design of B7 Semester IT University of Mumbai. Part 1 is already covered in previous lecture where we have discussed Enterprise Campus Requirement, Building Access Layer Design Consideration. In this part, we will going to discuss building distribution layer design and campus core design consideration. So these two considerations will be discussed in this part 2. Building distribution layer design consideration. The building distribution layer aggregates the building access layer, segments work groups, and isolate segments from failure and broadcast storm. This layer implements many policies based on access list and quality of services setting. The building distribution layer can protect the campus core network from any impact of building access layer problems and implementing all the organization's policy. When implementing building distribution layer, there are several questions like how many devices will each building distribution switch handle? What type of level of redundancy are required? How many uplinks are needed? What speed do the uplink need to be the building core switches? What cabling is currently available in the wiring closet? And what cabling options exist for uplink connectivity? As network services are introduced, can the network continue to deliver high performance for all its applications such as video on demand, IP multicast, or IP telephony? So, the network designer must pay special attention on performance, redundancy, infrastructure services, and best practice recommendation for optimal building distribution layer design. So let us discuss what is performance. Building distribution switches should provide wire speed performance on all ports. This feature is important because of building access layer aggregation on one side and high speed connectivity of the campus core module on the other side. Future expansion with additional ports or modules can result in the overloaded switch if it is not selected properly. So this is performance. Now come to redundancy. In redundancy, redundant building distribution layer switches and redundant connection to the campus core should be implemented using equal cost redundant connection to the core supports fast convergence and avoids routing black holes. Network bandwidth and capacity should be engineered to withstand node or link failure. When redundant switches cannot be implemented in the campus core and building distribution layer, redundant supervisors and the stateful switchover, that is SSO, and non-stop forwarding NSF technologies can provide significant resiliency improvements. These technologies result in 1 to 3 seconds of outage in a failover, which is less than the time needed to replace supervisor and recover its configuration. Depending on the switch platform, full image in service software update technology might be available such that the complete Cisco iOS software image can be upgraded without taking the switch or network out of service, maximize network availability. So these are the three important things. Now come to third, infrastructure services. Building distribution switches should not only support fast multi-layer switching but should also incorporate network services such as high availability, quality of services, security, and policy enforcement. Expanding and or reconfiguring distribution layers devices must be easy and efficient. These devices must support the required management features. With the correct selection of building distribution layer switches, the network designers can easily add new building access module. Multi-layer switches are usually preferred as building distribution layer switches because this layer must usually support network services such as quality of services and traffic filtering. There are best practice recommendations for optimal building distribution layer design. So these include use first hop redundancy protocol, deploy layer 3 routing protocol between the building distribution switches and campus core switches. If required, building distribution switches should support virtual LANs that span multiple building access layer switches. First recommendation is using first hop redundancy protocol. This diagram shows point-to-point interconnection between distribution switches. This is building distribution layer and this is building access layer, and these are the layer 2 switches and layer 3 switches. Layer 2 links and layer 2 links. So this is a symmetrical diagram and different things are there. If layer 2 is used between building access switch and building distribution switch, okay, building access and building distribution switch, convergence time when a link or node fail depends on default gateway redundancy and failover time. Building distribution switches typically provide first hop redundancy, that is default gateway redundancy. Using HSRP gateway load balancing protocol, this is GLBP, or virtual router redundancy protocol VRRP. GLBP and VRRP. What is GLBP? GLBP is Gateway Load Balancing Protocol or Virtual Router Redundancy Protocol. This redundancy allows a network to recover from the failure of the devices acting as default gateway for AND nodes on a physical segment. Uplink tracking should also be implemented with the first hop redundancy protocol. HSRP or GLBP timers can be reliably tuned to achieve sub-second, that is 800 to 900 millisecond convergence for link or mode failure in the boundary between layer 2 and layer 3 in the building distribution layer. In Cisco deployment, HSRP is typically used as the default gateway redundancy protocol. What is default? This is for Cisco. Okay, Cisco deployment. So HSRP is typically used as default gateway protocol. VRRP is an Internet Engineering Task Force standard. VRRP is IETF recommendation standard based method providing default gateway redundancy. More deployments are starting to use GLBP because it supports load balancing on uplink from the access layer to the distribution layer, as well as the fast hop redundancy and failure protection. So this particular figure shows one model that supports recommended layer 3 point-to-point interconnection between distribution switches. No virtual LANs span the building access layer switches across the distribution switches, so from an STP perspective, both access layer uplinks are forwarding, and no spanning tree protocol or STP convergence is required if the uplink failure occurs. Only convergence dependencies are the default gateway and return path route selection across the layer 3 distribution to distribution link. In this figure also, layer 2 virtual LAN number is mapped to layer 3 subnet for ease of management. Okay, so this is the thing. If layer 3 is used to the building access switch, the default gateway is at the multi-layer building access switch, and first hop redundancy protocol is not needed. Second recommendation is deploying layer 3 routing protocol between building distribution and campus core. In previous what we have seen, that is layer 3 distribution switch interconnection for first hop redundancy protocol. Now, uh, here we will see the layer 3 deployment. Routing protocol between the building distribution switch and campus core switches support fast, deterministic convergence for the distribution layer across redundant links. Convergence based on up or down state of a point-to-point physical link is faster than timer-based non-deterministic convergence instead of indirect neighbor or root loss detection using halos and dead timers. Physical link loss indicates that a path is unusable. Clear? All traffic is routed to the alternate equal cost path. For optimum distribution to core layer convergence, build redundant triangle, not square. Redundant triangle. Okay. For what? Optimum distribution to core layer. Fine. Build redundant triangle, not a square, to take advantage of equal cost redundant path for the best deterministic convergence. So here we have seen, we can see that triangle redundancy is provided with this graph and square redundancy is provided with this graph. So there is something. The multi-layer switches are connected redundantly with triangle of links that have layer 3 equal cost. Okay, that have a redundancy of equal cost. Because the links have equal cost, they appear in routing table and by default will be used for load balancing. Fine. If one of the link or distribution layer devices fails, convergence is extremely fast because the failure is detected in the hardware and there is no need for routing protocol to recalculate a new path. Already path is provided, so either use this triangle or use this triangle. Okay, so if one of the links or distribution layer devices fail, then the convergence is extremely fast. Why? Because the failure is detected in the hardware and there is no need for routing protocol to recalculate the new path. It just continues to use one of the path already in its routing table. In while on the right hand side, only one path is active by default because it is square. Okay, this is the path, no other path is there, so it just continues to use one of the path already shown in its routing table, and only one path is active by default, and link or device failure requires the routing protocol to recalculate a new route to convergence. In previous, it is not required because the entry is already there in routing table. Other related recommended practices are establishing routing protocol, peer relationship only on links that you want to use as transit links. And second recommendation is summarize routes from the building distribution layer into campus core layer. So this is third recommendation for optimal building access layer. This is supporting virtual LANs that span multiple building access layer. So here it shows layer 2 and trunk, RSTP protocol, layer 2 links are there, HSRP active and HSRP root VLAN, and standby and secondary root VLAN, and building access, building distribution layer. So it clearly divides the building access in. Whenever we are representing building access layer, it uses layer 2 switches layer, and multi-layer switches are there in the layer 3, and router is also attached with this. So in a less than optimal design where virtual LANs span multiple building access layer switches, the building distribution switches must be linked by layer 2 connection. Okay, it must be linked by layer 2 connection, or building access layer switches must be connected via trunks. Both the things are used here. The design is more complex than when a building distribution switches are interconnected with layer 3. Spanning tree protocol convergence is required if uplink failure occurs. So in this particular figure, there are some recommendations for use in this suboptimal design. First thing is use RPVST plus as the version of STP. Then second recommendation is provide a layer 2 link between the two buildings. Distribution switches to avoid unexpected traffic path and multiple convergence events. If you choose to load, third recommendation is if you choose to load balance virtual lens across uplinks, be sure to place the HSRP primary and RPVST plus route on the same building distribution. Okay, on the same RPVST plus on the same. Fine. Same building distribution layer switch to avoid using the inter-distribution switch link for transit. So this is how we can use the recommendation for optimal building access layer design. Now come to campus core design consideration. There are different things. Campus core design considerations. Low price per port and high port density can govern switch choice for wiring closet environment, but high performance wire rate multi-layer switching devices, the campus core design. Using campus core switches reduces the number of connections between the building distribution layer switches and simplifies the integration of server farm module and enterprise edge module. There are five different topologies, so you must know all these five. Campus core switches are primarily focused on wire speed forwarding on all interfaces and are differentiated by level of performance achieved per port rather than a high port density. Okay. So as a recommendation practice, deploy a dedicated campus core layer to connect three or more buildings in the enterprise campus or four or more pairs of building distribution switches in a very large campus. Campus core switches are typically multi-layer switch. Okay, campus core switches are typically multi-layer switch. Using a campus core makes scaling the network easier. For example, with a campus core, new building distribution switches only need connectivity to the core rather than the full mesh connectivity to all other building distribution switches. One more important thing, not all campus implementation needs a campus core. Okay, it is the campus core is not required everywhere. As already we have seen that the campus core and building distribution layer can be combined at the building distribution layer in smaller campus in second unit. So let us discuss issues to consider in campus core layer design, including the performance needed in the campus core network. Second is the number of high capacity ports for building distribution layer aggregation and connection to the server farm module or enterprise edge module. Then high availability and redundancy requirement to provide adequate redundancy at least two separate switches ideally located in different buildings should be deployed. So these are the issues. Another core campus consideration is enterprise edge and WAN connectivity. For many organizations, campus core provides enterprise edge and WAN connectivity through edge distribution switches connected to the core. However, the large enterprise with data center, the enterprise edge and WAN connectivity are aggregated at the data center module. Typically, the campus core switches should deliver high performance, okay, switching multi-layer switching solution for enterprise core campus and should address the requirements like gigabit density, data and voice integration, LAN, WAN and metropolitan area network convergence, scalability, high availability, intelligent multi-layer switching in the campus core and the building distribution and server farm environments. Large campus design. In this large campus design, building access layer is there, building distribution layer and campus core layer. In campus core layer, this uses multi-layer switches. Building distribution also uses multi-layer switches. In junction of building distribution layer, it uses layer 2 switches and the system connected to here. For large campus, the most flexible and scalable campus core layer consists of dual multi-layer switch. Okay, so dual multi-layer switch in the building distribution as well as a campus core layer. Multi-layer switch campus core layer have several best practice features. These includes reduced multi-layer switching, peering, routing adjacencies. Each multi-layer building distribution switch connects to only two multi-layer campus core switches using a redundant triangle configuration. This implementation simplifies any-to-any connectivity between building distribution and campus core switches and is scalable to arbitrarily large size. It also supports redundancy and load sharing. Okay, redundancy and load sharing. Then topology with no spanning tree loops. These loops are very dangerous always. No short STP activity exists in the campus core or on the building distribution links to the campus core layer because all the links are layer 3, that is routed links. Arbitrary topology are supported by the routing protocol used in the campus core layer because the core is routed. It also provides multicast and broadcast control. Fine. And next is improved network infrastructure service support. Multi-layer campus core switches provide better support for intelligent network services than data link layer core switches could support. So this whole design maintains two equal cost path for every distribution network. You can see here clearly. Thus, recovery from any link failure is fast and load sharing is possible, resulting in high throughput in the campus core layer. One of the main consideration when using multi-layer switches in the campus core is switching performance. Multi-layer switching requires more sophisticated devices for high-speed packet routing. Modern layer 3 switches support routing in the hardware even even though the hardware might not support all the features. If the hardware does not support a selected feature, it must be performed in software. This can dramatically reduce the data transfer, like access list might not be processed in hardware if they have too many entries, resulting in switch performance degradation because of very low memory or memory constant. It is not able to process the whole list. Small and medium campus design option. Previous one is large campus design. Now small and medium campus design option. So here you can see that in case of a small campus network, building access switching are there and building distribution and campus core is clubbed together and the devices are connected, different devices. These are the layer 2 switches and server is associated with this and one more server is associated with this. So this is how a small campus network is designed. A small campus or large branch network might have fewer than 200 end devices and the network servers and workstation might be connected to the same wiring closet. Because switching in a small campus network design may not require high-end switching performance or much scaling capability. In many cases, the campus core building distribution layer can be combined into a single layer, which is you can already seen in this particular figure. This design can scale to only a few building access layer switches. Or low and multi-layer switch provides routing services closer to the end user when multiple virtual LAN exist. For example, for a very small office, one low and multi-layer switch may support the LAN access requirement for the entire office. And for medium-sized campus network, you can see that this is the building access switching and building distribution and campus core. It is also attached and it is clubbed together and there is one server and two multi-layer switches are connected and two layer 2 switches are connected. Okay, so how this can be achieved? Here in a small network, only one multi-layer switch, and it is here building distribution and campus core is clubbed together. Here two multi-layer switches are there connected to a server. Two different servers are there and single server is there. In model design, it is not necessary that this type of design exists for each and every medium campus network design. For a medium-sized campus with 200 to 1000 end devices, the network infrastructure typically consists of building access layer switches with uplink to building distribution or campus core multi-layer switches that can support the performance requirement of a medium-sized campus network. If redundancy is required, redundant multi-layer switches connected to building access switches, uh, providing full link redundancy as shown here. Is distribution at the campus core. So here in this particular campus core is distribution. Enterprise is consist of e-commerce module, internet connectivity module, WAN and MAN site-to-site VPN module, and remote access and VPN module. So this module is very open to the end user. And in campus core, there are core layer and edge distribution layer. So it uses multiple multi-layer switches. So let us discuss. And it is already discussed in previous unit that enterprise edge module connects to the campus core directly or through optimal edge distribution module. So it is shown in this figure. The edge distribution multi-layer switches filter and route traffic into campus core, aggregates enterprise edge connectivity, and provide advanced services. Switching speed is not as important as the security in the edge distribution module, which isolates and controls access to the device that are located in the enterprise edge module, like servers in an e-commerce module or public servers in the internet connectivity module. These servers are closer to the external users and therefore introduce a higher risk to the internal campus to protect the campus core from threats. The switches in the edge distribution module must protect the campus from the uh, unauthorized access, IP spoofing, network reconnaissance, and packet sniffers. So these are the four different attacks. First is unauthorized access. All connection from edge distribution module that pass through the campus core must be verified against the user and user's right. Filtering mechanism must provide the granular control over the specific edge subnets and their capability to reach areas within the campus. Now come to IP spoofing. Okay, IP spoofing is a hacker's technique for impersonating the identity of another user by using that user's IP address. Denial of service attacks use IP spoofing to generate requests to server using the stolen IP address as a source. The server therefore does not respond to the original source, but it does respond to the stolen IP address. A significant amount of this type of traffic has attacked servers to be unavailable, thereby interrupting business. Denial of service attacks are a problem because they are default to they are very difficult, not default. They are very difficult to detect and defend against attackers and can use a valid internal IP address for the source address of IP packet that produce the attack. Network reconnaissance Network reconnaissance or discovery sends packets into the network and collect response from the network devices. These responses provide basic information about the internal network topology. Network intruders use the approach to find out about network devices and the services that run on them. Therefore, filtering traffic from network reconnaissance mechanism before it enters the enterprise network can be crucial. Traffic that is not essential must be limited to prevent a hacker from performing network reconnaissance. And last attack is packet sniffers. Packet sniffers are devices that monitor, capture the traffic in the network and might be used by hackers. Packet belongings to the same broadcast domain are vulnerable to capture by packet sniffers, especially if the packets are broadcast or multicast, because Most of the traffic to and from the edge distribution module is business critical. Corporations cannot afford this type of security lapse. Multi-layer switches can prevent such an occurrence. The edge distribution devices provide the last line of defense for all external traffic that is destined for the campus infrastructure module. In terms of overall functionality, the edge distribution switches are similar to the building distribution layer switches. Both use access control to filter traffic, although the edge distribution switches can rely on the enterprise edge module to provide additional security. Both modules are multi-layer switching to achieve high performance, and but edge distribution module can provide additional security function because its performance require might not be as high. When the enterprise introduces a significant data center rather than a simple server farm, remote connectivity and performance requirement are more stringent. Edge distribution switches can be located in the data center, giving remote users easier access to corporate resources. Appropriate security concerns need to be addressed in this module. So, in this unit, we have covered building distribution layer design consideration that includes using first hop redundancy protocol, deploying layer 3 routing protocol between building distribution and campus core switches, supporting virtual LANs that span multiple building access layer switches. Then campus core design consideration. It includes large campus design, small, medium, and edge distribution at the campus core. In next video, we will discuss enterprise campus design part 3. So thank you very much. Bye bye for now. Have a nice day. Have a nice time.